Hi everyone, today I will be presenting on the topic of color science and applications with a specific focus on the change of perceived chroma and hue of object colors at different lighting levels due to the Hund effect. To understand color science, we need to start with the fundamentals of color coordinates and how the human eye perceives colors. By studying how colors are quantified and how our eyes perceive them, we can gain insights into the complexity of color perception. Our topic aligned with the CIE Research Strategy 2023, emphasizing the importance of color accuracy and standardization. Human eye perceives color through photoreceptor cells in retina called rods and cells. Rods are responsible for vision in low light, while cones are responsible for color vision and function best in bright light. These are three types of cones, L, M, S cones, each sensitivity to different wavelengths of light. This slide shows the cone absorption curve, which represents the proportion of light observed at each wavelength by different types of cones. Understanding these curves helps us understand how colors are perceived under different lighting conditions. This is the spectral power distribution of typical daylight from sun, and this is the spectral reflectance curve of the material we want to see. And this is the sensitivity of our cone cells. And this is finally the color what we see. The luminous efficiency function by CIE shows the sensitivity of the human eye to different wavelengths of light. The photopic curve represents daylight adapted response, most sensitive to green, involving cones. The scotopic curve represents dark adapted response shifted to shorter wavelengths, involving rods. The next step is the color coordinates. Color coordinates help us organize colors in three-dimensional system using parameters like hue, chroma, and lightness. This organization allows for precise and consistent communication of colors. The CIE 1931 standard observer is based on the fovea where vision is sharpest, approximately 2 degrees from the optical axis. However, this standard does not accurately reflect observations in short wavelengths. To address this, the CIE introduced the 10-degree standard observer. Actually, not all colors could be generated using CIE's three RGB primary colors. Due to the limitations, CIE defined three imaginary measurement values as primary color stimuli. All real colors can be represented by mixing three tri-stimulus. XYZ measurement values are called CIE standard tri-stimulus values. Here. We can transform the RGB to XYZ primary color stimuli as well. Here. As I commented, CIE 1964 standard observer corresponds to a large field of vision the size of A4 page at a standard viewing distance of 30 centimeter. New color matching functions were standardized, providing a more accurate representation of human color perception. CIE standard colorimetric system uses standard color matching functions X bar, Y bar, Z bar of the standard observer, converts the spectral curve into three values X, Y, and Z, determining the colors. Color of an object or light source determined using X, Y, Z. This is the spectrum from the sun, and this is the object, the reflectance of the object, and this is the cone cells sensitivity. We can then, if we integral each sensitivity from the over the wavelength, then we can get the X and Y and Z. The chromaticity diagram according to the CIE standard colorimetric system CIE 31. Requirements for the precise color classifications, radiation distribution E, and reflectance of the object R, and color matching function X bar, Y bar, and Z bar. This is the example of the mathematical formula for X. This slide shows the chromaticity diagram according to the CIE standard colorimetric system, CIE 31. The purpose of it is to represent the three-dimensional color space in a two-dimensional diagram. It allows color specifications to be determined separately from lightness. Chromaticity coordinate x, y, z is normalized by this formula, and z is unnecessary as z is 1 minus x minus y. I missed the comma here. CIE 31 standard. It uses the tri-stimulus values x, y, z to determine color with high precision. X and z values are different to approximately for hue and chroma in visual chromaticity diagram. The spectral locus. This is it. Concave curve of pure colors in the visible spectrum, shaped like a sole of a shoe. Neutral achromatic point here, white point, x is 0.33 and y as well for equal energy light sources. It could be changed by the illuminant type of the source. Color definition by hue and chroma. Equal Q wavelength corresponds to the additive color mixing for the required color. Chroma is the percentage of pure color in mixture. The highest chroma is 1 and lowest is 0. This is the CIE lab color space developed in 1976 based on CIE 1931 tri-stimulus coordinate XYZ for uniformity and simplicity. It provides a uniform scale is device independent. Each perceivable color is defined by coordinates L star, A star, and B star. A star is lightness here, and A star is here, red and green axis, and B star is here, blue and yellow axis. Actually, from here to here, it means the chroma. Transformation formulas for CIE lab color space convert the XYZ values into L star, A star, and B star values. These formulas help in understanding the color properties in a perceptual uniform space. The characteristic of the CIE lab color space. It is characterized by being an Euclidean space with coordinates Aristotle, A star, and color coordinate systems. It is perceptually structured to correspond to the evolution of our understanding and ability to measure and represent colors colorimetric from earlier experiments to modern space color spaces. These systems have significantly advanced color science. The second chapter is the topic I choose, which is the change of perceived chroma and hue of object colors at different lighting level due to Hund effect. Hund effect describes how objects appear less saturated under lower indoor lighting compared to outdoor daylight. Previous studies confirmed this effect for red and green colors. Our objectives are to quantify changes in perceived chroma and hue for red, green, yellow, and blue at different lighting level. Experimental procedure is gray patches were used to ensure proper eye adaptation. Participants then matched test patches to reference patches under different lighting conditions. This procedure helped in accurately measuring the perceived changes in chroma and hue. The result shows that the chroma was perceived 8% to 15% lower at 100 lux compared to 1000 lux. Hue angles also shifted slightly, with green showing the greatest chroma change and yellow the least. Statistical analysis confirmed significant effects of patch color and lighting condition on chroma and hue perception. Scattered below is color coordinates for the patches with the light and 3000K and 1600K. X marks show the reference patches and the circles show the test patches. The colored circles are the patches chosen by subjects. The black filled circles with error bar are the mean coordinate for matching patches of. And this is the graph which are the relative chroma differences left here and the hue difference here for similarly 3000 and 6500K. Each bar shows the normalized mean chroma difference between the reference and chosen matching patch. Error bar shows the standard error. The conclusion is the Hunt effect significantly affects perceived chroma and hue. These findings can help develop new color fidelity models that consider lighting conditions, ensuring accurate and consistent color perception in various environments. This chapter is for application of the topic. Uh, Uh, it has practical applications in lighting design, helping to improve lighting conditions to enhance perceived color saturation. It is useful in commercial spaces, galleries, and museums to improve the appearance of displayed object. Especially, I think it's possible to use the specific color to object under a certain lighting condition to reproduce the outdoor daylight condition. In display technology, this study enhances the accuracy of color reproduction in digital displays by considering ambient lighting conditions. It helps in calibrating display devices for consistent color perception under different lighting environments. The final chapter is technical and scientific issues. Mm. There are technical and scientific issues to address. Developing new color fidelity metrics that accurately reflect the Hund effect is essential. This involves quantifying color changes under various lighting conditions and incorporating these changes into evaluation criteria. Additionally, optimizing lighting conditions for consistent color perception is crucial. Thank you.